Good afternoon, teachers. My name is Kyler. Today, me and my group mates Dani, Kish, and Satana will be presenting our ASML Project 1.
Okay, so today I'll be introducing you to the materials commonly used in aircraft manufacturing. So in general, there are 8 main materials used in aircraft constructions. These materials have been selected based on their strength, weight, corrosion resistance, and also the ability to withstand extreme conditions. So the 8 materials are steel, aluminium, titanium, copper, nickel, magnesium, and composite materials. So steel, we usually use it in high stress components like maybe the landing gear, engine mounts. This is mainly because of its high strength and durability. Aluminium is not very common nowadays. It's usually, if it is used, it's usually used in the fuselage and wing structures for the strength to weight ratio and also the corrosion resistance. For titanium, it is usually used in high temperature areas such as maybe the engine and structural reinforcements because of its heat and corrosion resistance. Copper is usually used in electrical systems and wiring due to the conductivity. Nickel, like titanium, is also used in high temperature components like the engine because of its ability to withstand extreme heat. Magnesium is a lightweight metal used in some aircraft parts, but the application is limited because of its risk of catching fire. Composite materials is sort of a breakthrough in modern aircraft design, mainly for the aircraft that we will be talking about later on in the slides, the Boeing 777 Dreamliner, where carbon fiber composites significantly reduce weight and improve overall performance efficiency.
So now how are aircraft advanced composite materials manufactured? For aircraft like the Airbus A350, Boeing 787 and Boeing 777X, advanced composite materials are primarily carbon fiber reinforced with resin. Autoclaves or out-of-autoclave processes such as resin transfer molding are used to cure these materials after they have been laid out in molds utilizing automated fiber placement techniques. To guarantee integrity, quality control techniques like the ultrasonic testing are used once the material has been solidified. Ultimately, during the assembly process, these components are fused together, providing the airplane strength and lightness. So now we'll see the development of materials in aircraft applications. Why is there a push for composite materials in the aviation industry? Well, composite materials are important to the aviation industry because they provide structural strength comparable to metallic alloys but at a lighter weight. This leads to improved fuel efficiency and performance from the aircraft. As the aviation industry increasingly focuses on sustainability, composites play a crucial role in achieving environmental goals. Composites are a crucial part of aviation's future because they reduce emissions and increase fuel efficiency, which supports initiatives to lessen the sector's carbon impact. Modern airplanes that heavily rely on composite materials to accomplish these benefits include the Airbus A350, Boeing 787 and Boeing 777X.
Composite materials plays a crucial role in modern aircraft, which is offering high strength, low weight, and excellent durability. Here are some of the most commonly used composite materials in aircraft industry. Composite honeycomb structure, carbon fiber reinforced polymer, fiberglass reinforced polymer, and finally aramid fiber reinforced polymer, which is Kevlar composites. Now let's take a look at some of the most commonly used composite materials in aerospace. Firstly, we have the composite honeycomb structure. This material has thin face sheets attached to a hexagonal honeycomb core, which is usually made of aluminum, fiberglass, or Nomex. It's perfect for applications that need to be lightweight but still strong. Plus, it absorbs energy well, making it durable and impact resistant. On top of that, it's highly resistant to corrosion and fatigue, which is why it's widely used in aviation components. Next up, carbon fiber reinforced polymer or CFRP. This is a super durable material made of high strength carbon fiber bonded to a polymer matrix, usually epoxy resin. What makes CFRP so popular is its incredible strength to weight ratio. It's much stronger than steel but way lighter. It's also highly resistant to corrosion and fatigue, which helps maintain an aircraft's structural integrity over time. And since it's so lightweight, it also improves aerodynamics and reduce fuel consumption, which making it a game changer in aerospace engineering. These composite materials have transformed modern aircraft, making them stronger, lighter, and more efficient. And that's why they are important in the aerospace industry today. Now, let's talk about fiberglass reinforced polymer or FRP. This composite is made by embedding fiberglass strands into a polymer matrix, which is usually polyester resin or epoxy. It has a great strength to weight ratio and compared to carbon fiber reinforced polymer CFRP, it, it is a more budget friendly option. Plus, it's highly resistant to chemicals, moisture, and corrosion, and making it a reliable choice for long term aircraft applications. Nextly, we have aramid fiber. This material is even lighter than fiberglass and has excellent fatigue resistance, making it ideal for aerospace use. One of its standout features is its superior fire and heat resistance, which is improved safety in high temperature conditions. On top of that, it has excellent vibration dampening properties, which help reduce noise and enhance passenger comfort during flights. Both of these materials contribute significantly to modern aircraft design, offering durability, safety, and efficiency. Now, where exactly can we find composite materials in an aircraft? Let's take a look. Firstly, we have the fuselage, which often used carbon fiber reinforced polymer. This material is used for structural elements and skin panels, providing reduced weight, improved strength, and long term durability. Since CFRP is much lighter than aluminum, it helps improve the aircraft loading capacity and fuel efficiency. In fact, it's about 25% lighter than traditional aluminum constructions, which not only improve aerodynamics but also lowers operational cost. Nextly, let's talk about the landing gear. This is another area where CFRP is widely used. One of its biggest advantages is its ability to withstand numerous takeoffs and landings without excessive wear, ensuring long-term endurance. Plus, it's also strong yet lightweight design reduce maintenance need and boost overall aircraft performance. These are just a couple of examples, but composite materials can be found in many parts of an aircraft, making them an important part of modern aviation technology. Alright, now let's talk about two more key areas where composite materials play a major role in aircraft design. First up, the nacelles, basically the engine housings. These use nano reinforced carbon fiber, which is a game changer in aerospace engineering. It's not only improve aerodynamics by reducing drag but also provides extra protection to the engine components. Since it both stronger and lighter than traditional materials, it helps lower the total weight of aircraft. And in aviation, every bit of weight savings counts when it comes to fuel efficiency, and overall performance. Now let's move to the wings and their components. This is where glass fiber reinforced polymers come into play. They provide a solid and sturdy foundation for important wing structures like ribs, leading edges, spars, and wing skins. Compared to traditional metal wings, GFRP is not only stronger but also much more resistant to fatigue. This means the wings last longer, requires less maintenance, and help cut down on long-term operational costs. Plus, since wings take on a lot of stress during flight, using a material that can withstand the pressure while keeping the aircraft lightweight is a huge advantage. So, whether it's improving aerodynamics with lightweight engine housings or enhancing wing durability with advanced composites, these materials are shaping the future of modern aircraft.
In recent developments of new cutting-edge materials, there has been a new component developed by NASA called silicon carbide fiber reinforced ceramic matrix composite. It is a lightweight, high-strength composite capable of withstanding temperatures up to 2700 Fahrenheit. It is also ideal for high-performance aircraft engine components with high durability in extreme conditions, which allows extended service life and reduced maintenance. It is also integrated in various aerospace applications to enhance performance and efficiency. This is our group's version of materials usage on a Boeing 787 Dreamliner. For the fuselage, the material that is best used for it is the CFRP. Why? CFRP offers a high strength to weight ratio compared to other materials like aluminum, so this allows significant weight reduction. CFRP is also flexible and allows smoother aerodynamic profiles that reduces drag and improves fuel efficiency. CFRP is also not susceptible to corrosion, and that lowers the cost of maintenance and lower airframe life. Other than that, it has superior fatigue properties, and that allows the fuselage to withstand repetitive pressurization cycles without significant degradation. For the cabin, we decided that the material that's best used for it is the Basotec developed by BASF. It has a density of 6 grams per liter, which is 30% lighter than conventional Basotec foams. This allows the aircraft to have a higher fuel efficiency. Basotec also has a super acoustic insulation which provides high sound absorption capacity, reducing cabin noise levels. This will allow a quieter and more comfortable environment for passengers. Basotec also has inherent flame retardant properties that meets the stringent fire safety standards required in aviation applications.
The wings. So for the wings of the 787 are primarily made of carbon fiber reinforced polymer composites, accounting for about 50% of the aircraft's total structure. Unlike the traditional aluminium, the 787 wings use carbon fiber reinforced plastic. This material is strong, lightweight, and highly flexible. The aircraft is 50% composite and by weight and 80% by volume. Why carbon fiber reinforced polymer? It's because of the high strength to weight ratio, corrosion and fatigue resistance, aerodynamic efficiency through smoother surfaces, greater flexibility allowing for a more efficient wing shape during flight. Next, I'll be talking about how the Boeing 787 achieves exceptional wing flex. One of the primary reasons for designing wing flexibility is to enhance aerodynamic. Wing flex allows the wing to adapt to varying airflow conditions during flight. Unlike rigid wings which can create turbulence and drag, flexible wings adjust dynamically, reducing drag, allowing for smoother airflow. Next is advanced engineering. Engineers design the wings to handle both normal and extreme flight conditions. The flexibility helps the wings to adapt to changing air pressures and forces during flight. Rigorous testing. Before the 787 was certified, its wings underwent extreme stress tests. Boeing bent the wings far beyond their operational limits to ensure safety and durability. Now I'll be talking about pylon. So what is pylon? A pylon in aviation is the structure that connects the aircraft engine to the wing or fuselage. It serves as a mounting point for the engine and plays a crucial role in load transfer, aerodynamic and heat resistance. The pylons of the Boeing 787 Dreamliner serves as a structural attachment between the engines and the wings. So for the pylon materials, they have titanium alloys. Titanium alloy is the primary material used in 787 pylon, chosen for its high strength to weight ratio, corrosion resistance, and ability to withstand high temperatures from the engine. Titanium is particularly useful in areas exposed to hot engine exhaust and thermal cycling. Next is the aluminum alloys. Used in less heat-intensive areas of the pylon structure, provides lightweight strength while being easier to manufacture and maintain. Next is the nacelles. What is a nacelle? A nacelle is a streamlined casing that surrounds an aircraft engine, improving aerodynamic, reducing noise, and protecting the engine components. On the Boeing 787 Dreamliner, nacelles helps manage airflow, minimize drag, and enhance fuel efficiency. Typically mounted on the wings of fuselage, they may also include thrust reversers to assist in braking during landing. Next, the different parts of the nacelle of the Boeing 787 are made from varied materials based on their function. Carbon fiber composites for lightweight strength, titanium for heat and impact resistance, and nickel-based alloys for high temperature durability in the exhaust section. Now, I will tell you the Boeing 787 nacelle materials. Firstly, we have the inlet air intake. CFRP and titanium directs airflow. CFRP reduces weight and titanium reinforces the leading edge for impact resistance. Next is the fan cowl. CFRP protects the engine fan, lightweight and durable. Next is the thrust reverser. CFRP, titanium and aluminium redirects the thrust for braking. CFRP for weight saving, metal for strength. Next is the aft nacelle and exhaust. Titanium and nickel alloys withstand high heat and directs exhaust gas. Lastly is the chevrons. CFRP or titanium reduces engine noise with serrated edges.
So now I'll be discussing the empennage of the Boeing 787 Dreamliner and why it is primarily constructed using carbon fiber reinforced polymer, or easily known as CFRP composites. The empennage, or easy to say, the tail section of the 787 Dreamliner, is made almost entirely of CFRP composites. This choice of material offers quite a few key advantages over traditional materials like aluminium. First of all, high strength to weight ratio. CFRP composites provide quite exceptional strength while being significantly lighter than metals, which reduce the overall weight of the aircraft. Secondly, the fatigue resistance. Unlike metals, CFRP does not suffer from fatigue cracking, making it more durable over longer operational periods. We move on to lower maintenance requirements. The composite structure also requires less maintenance compared to metals such as aluminium, which is prone to corrosion and fatigue damage. This is linked to the second point. And lastly, the improved aerodynamic efficiency. The lightweight nature of CFRP contributes to better fuel efficiency and performance by reducing drag and optimizing the aircraft's center of gravity. Now we'll move on to uh, the stabilizers. Stabilizers are also made of CFRP like many other parts. This is mainly because CFRP is extremely lightweight, more so than traditional materials like titanium or aluminium. This low weight reduces fuel consumption, which improves efficiency and also can extending the range of the aircraft. CFRP is also fatigue resistant, which leads to a longer service life, which is particularly useful for stabilizers which experience constant loading during the flight. Okay, so now we move on to the flight controls. This is a bit more exciting because flight controls use a mix of materials. The main one is still CFRP, but there is also titanium being used. CFRP makes up the primary flight controls such as the elevator, rudder, ailerons, slats, flaps, and also the spoilers. Titanium is used in areas which are prone to high stress, like the actuator points, brackets, and also the hinges. This is mainly because it's very strong and durable.
Now, let's talk about one of the most crucial parts of an aircraft, which is the landing gear. This component supports the entire weight of the aircraft during takeoff, landing, and taxiing, so it needs to be extremely strong and durable. Titanium is one of the key materials used in landing gears. It helps with weight optimization, meaning it keeps the landing gear strong without making it too heavy. It has an excellent strength to weight ratio, making it both tough and lightweight at the same time. Plus, titanium is highly resistant to corrosion, which is super important since landing gear is constantly exposed to harsh weather and environmental conditions. Another major advantage is that it can endure extreme stress and pressure without deforming, ensuring long-term reliability. In addition to titanium, strong steel alloys like 4340 steel are also used for landing gear, beams, and struts. These alloys offer exceptional tensile strength and toughness, making them perfect for handling the heavy loads that occur during landing. Since landing gear observes a huge amount of force when the aircraft touches down, using a material with high durability is absolutely important for safety and performance. With the combination of titanium and high strength steel alloys, landing gear are designed to withstand immense pressure while remaining lightweight and reliable, ensuring smooth and safe landings every time.
Then let's take a look at the nose landing gear, which is another important part of the aircraft landing system. While it doesn't bear as much weight as the main landing gear, it still plays a crucial role in steering and supporting the aircraft during takeoff, landing, and taxiing. One of the key materials used in nose landing gear is high-strength aluminum alloys. These are mainly used in non-load bearing components such as fairings and covers. The reason aluminum alloys are a great choice is that they offer a balanced strength to weight ratio. This helps reduce the overall weight of the landing gear while still being strong enough to handle operational stress. Plus, they can sustain weight without deforming and making them reliable for long term use. Another important material used in nose landing gears is carbon fiber reinforced polymer or CFRP. This composite is incredibly weight efficient, which contributes to better fuel economy. One of its biggest advantages is its expeditional resistance to corrosion and wear, meaning it can withstand harsh environmental conditions without fail. What makes CFRP even more valuable is that it significantly reduces weight without sacrificing strength and ensuring the landing gear remains both durable and lightweight. By combining high strength aluminum and CFRP, nose landing gears achieve the perfect balance of strength, durability, and weight efficiency, making them important for safe and smooth aircraft operationals.
And finally, our group reflection on aircraft materials in aviation and their impacts. The adoption of advanced materials in aviation, such as composites, titanium, and aluminum alloys, has revolutionized aircraft design. The shift from traditional aluminum structures to carbon fiber reinforced polymers, or CFRP, in modern aircraft like the Boeing 787 and Airbus A350 has significantly reduced weight, improved fuel efficiency, and enhanced durability. These materials resist corrosion and fatigue, leading to lower maintenance costs and longer aircraft lifespans. Additionally, titanium and nickel-based alloys play a crucial role in high-temperature areas, ensuring engine reliability and safety. However, challenges remain, including higher production costs, complex manufacturing processes, and recyclability concerns. Despite this, the aviation industry continues to embrace lightweight, high-strength materials to achieve greater fuel savings, lower emissions, and improve sustainability, shaping the future of air travel. We thank you for your time.